Hello everyone, my name is Parag Vijay Pawar and I am BSc Honours Student in Data Science and Artificial Intelligence at the Indian Institute of Technology, Guwahati. Today I will be presenting my term project titled Directional Manifold Steering in Crystal Diffusion Transformers via Parameter Efficient Weight Decomposition for Inverse Material Design. Please note that this work was conducted under my undergraduate summer research fellowship at Amity University, Noida and is currently in the process of drafting and under review. This research was guided by my mentor Dr. Dhruv Sharma at the Amity Center of Artificial Intelligence. So let's get started. Let us address the core problem. Traditional computational screening relies on density functional theory, which scales cubically and severely bottlenecks novel semiconductor discovery. In contrast, inverse design forces generative models towards the precise electronic targets. However, doing this natively places immense artificial energy gradients on the network structural weights, causing what is known as manifold drift. As you can see in this visualization, heavy property conditioning pushes the reverse diffusion trajectory completely off the manifold of physically valid structures. This results in chaotic atomic collisions, high energy unstable lattices, and a severely degraded discovery yield. To build our solution, we programmatically retrieved 33,432 unique, stable, non-metallic inorganic compounds from Materials Project API. This strictly constrained the data to band gaps between zero point 0.1 to 4 electron volts and the energy above Hull thresholds of less than 0.05 electron volts per atom. We then encoded the atomic numbers into the normalized 2D continuous space and serialized everything into the PyTorch tensor for memory efficiency. Our generative framework utilizes the Crystal DiT architecture, PyTorch, and Python. For our optimization and steering, we integrated both DoRA and LoRA adapter modules to compare their effectiveness with Adam Optimizer. Finally, we use MatGL, Magnet, and BioMagZen as our empirical evaluation oracles. Let me walk you through the code. So these as you can see on my screen, to test our manifold steering mechanisms, we implemented both standard LoRa and weight decomposed DoRA as shown here in our custom DoRA linear class. While LoRa linearly couples parameters, DoRA mathematically decomposes the weight updates. We freeze the base weights and explicitly isolate the learnable directional components from the magnetic vector. Moving to the training loop, you can see how we apply the core of our manifold steering mechanism, which is the classifier-free guidance or CFG, by injecting a 15% dropout mask on the target properties here in the code. We force the model to build a highly stable unconditional prior alongside its conditional mapping. Finally, to guarantee magnitude stability during backward passes and prevent structural collapse, we implemented strict gradient clipping at maximum norm of 1.0, executed here before our Adam with weight decay optimizer step. With the code established, let's contextualize the methodology. Our Crystal DiT backbone operates directly on continuous fractional coordinates, successfully bypassing heuristic heavy latent graph bottlenecks. Our objective was to deliver physically constrained crystal candidates without destroying the pre-trained thermodynamic prior. This flowchart perfectly illustrates our comparative findings. As you can see, standard LoRa linearly couples parameters, meaning amplified guidance induces weight norm inflation, driving the trajectory of manifold. DoRA's decomposition, however, acts as an orthogonal projection that forces gradient updates tangent to hypersphere, preserving the prior. Crucially, we replace the standard mean squared error, which quadratically penalizes transient atomic collisions, with a gradient clipped smooth L1 Hubble loss. This mathematical bounding strictly caps massive gradient penalties caused by geometric outliers. This pipeline flowchart shows the full architecture from structural encoding to generative backbone, passing through the manifold steering engine, and finally empirical evaluation. You can see here our data statistical relationships are mapped here, illustrating the pre-training alignments between the electronic properties and structural features. Moving ahead, we deployed an 18 layer of 8 head Crystal DiT By utilizing our custom loss function, we drop tracking convergence elegantly down to 0.2712 for DoRA, outperforming the baseline LoRa trajectory. Our actual manifold steering mechanism engineered a continuous time reverse diffusion process. We initialize our time-decayed CFG scale aggressively at 3.0 to lock onto the targets early, then decayed it to 1.0. 1.0 in the terminal steps for pure physical statements. We also deployed 45% alchemical substitution engine to aggressively force compositional novelty. Now let's interpret the outputs. The histogram on the left shows thermodynamic stability of our novel crystals. The structure overwhelmingly settled below our maximum formation energy thresholds of 0.5 electron volts per atom. On the right, the steered bandgap distribution precisely reflects our electronic targets. Here are specific samples generated by both DoRA and LoRa alongside their Magiel predictions. Notice how generated structures like zinc carbonate and rubidium lead chloride accurately achieve their target bandgaps while maintaining negative or highly stable formation energies. When we evaluate the quantitative matrices, the difference between the adapters is clear. While both froze the core parameters and trained roughly 17.8%, standard LoRa optimization generated only 204 structures with 79.08% marginal S.U.N rate. Conversely, our advanced tiered DoRA pipeline generated 357 structures, maintaining 100% of structural validity rate. Also, DoRA discovered 295 approved crystals with an incredible peak marginal S.U.N rate of 84.68% and allied bandgap steering MSE of 3.3302 electron volt squared, outperforming LoRa across the board. In conclusion, our dynamic manifold steering engine utilizing a time-decayed CFG scale and a Hubble loss precisely guided generative trajectories. Furthermore, DoRA successfully decoupled weight magnitude to prevent the lattice collapse inherent in standard LoRa fine-tuning. This framework has immediate applications in accelerating solid-state energy storage, next-generation photovoltaics, and strategically supporting the India semiconductor mission. Moving forward, we are actively extending this framework by incorporating I3 parameter efficient implementations, evaluating full fine-tuning baselines, and integrating vision language models for advanced automated structural analysis. Thank you for your time.